Hello everyone and welcome back to another video. Superconducting qubits are one of the most promising platforms for quantum computation, and that's not the only reason why companies like IBM and Google are looking into those and building those architectures in their lab to actually create larger and larger quantum computers. However, there are certain limitations to this growth, and there are certain mechanisms that make it difficult from a physics point of view to grow and grow and grow these architectures. One of them is the so-called ZZ coupling, and I will explain later on in easier words what this is about and how that actually works. But today's company, which is called Planckian, an Italian company, I will talk a little bit more also about the company later, is trying to solve this issue. Not only they're not trying to solve this issue by eradicating it, by actually making use of it and creating a new kind of superconducting architecture that comes with a lot of interesting benefits. So if you are interested in the inner workings of superconducting qubits, if you might have worked with them already, or if you are interested in new potential ideas of how to scale those, then stay tuned for today's video as we are diving deeper into Planckian. And with that, here we are on their website. So it says Planckian Quantum Computers Reimagined at Scale. And the scale is actually being a large topic here. Is basically the main reason, the main problem identified, and the one that they are trying to tackle. So technology, Planckian is building the foundational technology for large-scale quantum computers. Our quantum processor integrates the established reliability of superconducting circuits with a groundbreaking approach to qubit control, enabling the development of highly scalable quantum computers. And we will learn in a second how that works. Then there's some information here about the company that we will look at the end of the video as per usual. Now, talking about the technology. So how does it work? What is visible here on the website? So scaling superconducting qubits while preserving performance is one of quantum computing's toughest challenges. We go beyond traditional brute force scaling by decoupling control from qubit count, enabling quantum computers to scale efficiently by design. Now, let's take a look at this second sentence and let's take it apart. So they go beyond traditional brute force. With that, they basically mean the scaling approach that other established players in the market are trying to follow right now, by decoupling control from qubit count, enabling quantum computers to scale efficiently by design. So decoupling control from qubit count. As of today, you might see these quantum computers. They're looking like chandeliers, right? You have these golden plates that are stacked on top of each other. And there's a lot of control lines going down there. So if you're zooming in, you see that there's a lot of stainless steel cables that are going from the upper stage, from the, let's say, ceiling of your chandelier all the way down to the chip. These are radio frequency control lines that are being used to initialize, to control, to run gates on your quantum chip. Now, as the number of qubits grows, the number of these control lines grows as well. And that actually creates a challenge. It creates actually multiple challenges. On the one side, you need to actually be able to run stuff on these control lines. So you need a whole lab full of radio frequency equipment to generate those signals, to drive those signals individually to your qubits. And basically every qubit that you adds another couple of control lines into your set. The other side to that is if you're thinking about the temperature. So usually these qubits, they run at millikelvin temperature. So this is 273 degrees Celsius below zero. So minus 273, which is very close to the absolute zero of temperature. And the cooling powers that you can achieve at these very low temperatures, at the lowest stages, so basically the lower end of your chandelier, they are very limited. So adding new lines also means you add new thermal conductivity to the top where the room temperature is sitting. And therefore, you are losing cooling capability. So you need to make those cryostats bigger, bigger, and bigger to actually keep growing the numbers of chips, to keep growing the numbers of lines. And adding one more line might only make a couple of milliwatt or microwatt down at the lowest stage, but it actually ends up in a couple of watts or kilowatts at the highest stage of cooling. So usually you put in kilowatts of cooling power or of electrical power to reach milli to microwatts of cooling power at the lowest stages. Now, that said, this approach seems to be challenging in terms of scalability. It might still be doable, right? You can create many of these systems, you can make them much bigger, but of course, the question is how sustainable is that? How much energy do you need to put in to actually keep those driving? And that's where Planckian is basically trying to tackle that by adding a different technology. They themselves coined it the conveyor belt in their paper, which is, I think, in PRA, so Physics Review A, American Physics Society publication, where they talk about how the actual technology layout looks like. And let's see if we can learn a little bit more about that here in the text. So, a radical approach to scalability. Today's quantum computers rely on dedicated control lines for each qubit. That's what I was saying, right? Resulting in dense wiring that degrades qubit performance, inflates system footprint and cost, and fundamentally limits scalability. Most solutions for wiring problems demand new hardware and not trivial engineering, making scalability harder, not easier. We are charting a new path. Our unique chip architecture uses shared control lines, drastically reducing wiring complexity while sidestepping the limits of conventional design. This approach enables a new generation of quantum computing systems built on the most advanced qubit platforms and designed to scale from day one. So essentially the idea is, okay, instead of having every single qubit sit on its individual control line, we now put all of them on a conveyor belt, and then we basically just control the conveyor belt instead of having to run every single qubit with its own kind of, with its own electrical setup. So, powered by a new way to compute, so that's now the, let's say, base technology. At the heart of our innovation lies a new control protocol, a new way to address and operate a qubit. Unlike traditional processors, in our chip, all qubits are addressed simultaneously. Through innovative engineering of qubit couplings, we exploit these globally broadcasted signals to selectively perform gate operations and move quantum information within the chip. We rethink information processing from first principles to increase hardware efficiency and fast tackle the path to scalable, error-corrected, application-ready quantum computers. Now, how does it work? In order to understand that, let's take a couple of steps back. So, if you have a single quantum system, let's say a hydrogen atom, you have those different energy levels, right? A hydrogen atom is at the core, it is one proton which sits in the nucleus. You have an electron that is basically sitting on an orbit around that. Now these orbits, they are in a classical thought, they are just circular trajectories. In the quantum mechanics idea, they are actually wave functions that are, let's say, spreading around the nucleus that are correlated to the probability density. So where do you actually find the electron? It's a probabilistic wave function. Now that said, there are different orbitals, right? So you can kick an electron from the lowest orbital, which is its ground state, the lowest energy that it can have, to a higher orbit. So it goes up into a higher energy level. Now on this higher orbit, it can then, let's say, it has a increased radius and it can run on there. And usually these, let's say, spectra, they are very well known for the different kind of atoms. So hydrogen ground state to excited state might be a very specific energy of X number of electron volts. Electron volts is how we measure the energy usually in quantum systems. Now, let's say you have two hydrogen atoms. What now happens is they kind of combine and they become a molecule, an H2 molecule, because it's energetically favorable for them. What happens there? Well, they basically combine their orbits, and with that we say they hybridize. So basically they start now to become one quantum system. So the one hydrogen atom feels that the other one is close, and for that also their orbits are changing. Now instead of having individual orbits which are evolving around the atoms individual, they now basically create a common orbit which has a different shape. And that also is reflected in the energy levels. So of course they change. You don't have the same excitation energies anymore because now you're changing the whole diagram of energy, which is also the reason why they hybridize, right? Because it's energetically favorable for them to create this bond. So effectively then they are, let's say, looking from the outside, similar to a helium atom where you have 2 protons and 2 electrons. Now you have the 2, there you also have neutrons, but here you have the 2 protons and they are now creating this bond. So we see that quantum systems individually might be very well defined, but as soon as they get close to each other, they might change, they hybrid. Now what happens if you create a superconducting quantum computing chip? Well, you are creating a qubit here, you are creating a qubit there. You have to connect them to some signal lines. And in some way, these qubits, they can talk to each other now, especially if they are sitting close to each other. There might be some capacitive coupling between those. If they share a common control line, they can talk to each other via the control line, so they can exchange information. And that's the ZZ coupling. This is something that in traditional superconducting quantum technology, in traditional superconducting qubits, is considered a unwanted thing. So that's why you try to separate them. That's why you put a lot of work in engineering them in a way that they don't have this crosstalk. Because it basically means that you are shifting the energy levels and that somehow your system is not as well defined anymore as it used to be. Now you have to change the way that you address those qubits, the way that you are addressing those qubits with control signals, because think about our hydrogen atom again. If you're exciting one state to a higher energy level, then okay, this state is now let's say different, and that even more becomes interesting in this variability of coupling. And let's take a step back and look into another system where this kind of coupling plays a role in a capacitive or electrostatic sense. Let's think about neutral atom computers. So in neutral atom computers, you have atoms that are sitting in something like a crystal lattice, usually a 2-dimensional one. So you have these electrons that are sitting in an array, basically all nicely lined up. And now what you can do is you can use laser pulses to actually excite them into Rydberg states. A Rydberg state is basically an excitation of an electron into a far out orbit. So now, instead of sitting in their little sides, one of these atoms has an electron that goes very, very far out on an orbit that basically already becomes as big as the lattice dimension itself. So the electron has now a probability function that overlaps with the other atoms that are, let's say, close by, with the neighboring atoms. And that's the Rydberg blockade. So basically by doing that, you are now creating a, let's say, electrostatic dipole moment. So your electron is now distributed out here. You are creating some electrostatic change in the vicinity of the atom, because depending on where the electron is, it might be that your neighboring atom is sitting now in an electric field between the electron that is very far out, the nucleus that is still sitting where it used to be, and the neighboring atom being somewhere in between, right? So now you're creating these electrostatic fields. Of course, it's all quantum, so it's wave functions. You don't have electrons that are, let's say, moving specifically around there, but let's say in this simplistic picture, it's kind of like that. And that shifts now the excitation level of your other atoms that are sitting around close by, and that's why they are blocked. So you cannot use the normal laser pulse that is tuned to have exactly the excitation frequency, because the surrounding atoms are blocked. So this is something that is being used actively in this neutral atom computing space to actually perform specific gates to couple atoms with each other, to create an entanglement between specific atoms. Now here, in this superconducting case, it's very similar, because what Planckian is basically trying to do, as far as I understand, is they're trying to create such a very strong coupling between those qubits. They have different types of qubits, type A, type B, and now these different types of qubits, they have different control signals. And basically what Planckian is doing now is they create, let's say by design, those states, these ZZ coupling modes that are shifting the energy levels and therefore blocking, for example, neighboring qubits. And with that, they can basically reduce the number of control lines that they need. basically this conveyor belt idea, right? You put all the qubits next to each other, but you can have them block each other from actually interacting with the control signal. And then on top of that, you can also do other things like, for example, a gate that uses 3 different qubits at the same time or reads out 2 qubits by using a third one, which makes it also interesting or efficient for specific kind of read out activities or algorithm controlled activity. So that's, let's say, the high level picture about it. Of course, there's more. So if you're clicking here on the resources, you can also find out more about that. You see here the different designs. You see the red and the blue qubits that are indicating the different types, and then these yellow boxed ones over here. And of course, there's a lot of information available here. I'm recording this in June of 2026, and you can see that here May 2026 is the latest news. Planckian welcomes Seth Lloyd as a founding fellow. But what is also very interesting is this publication here that I was referring to before. So first demonstration of dynamical blockade in transmon qubit enabling global control. This is from January 2026, so very recent. And that basically shows that the idea that is behind Planckian, the founding idea, is now kind of turning into experimental reality, that it has been tested, demonstrated, let's say the core concept on this specific setup here on this transmon qubit. Now, as a last thing, let's quickly check out the team. And I have to say, I mean, my job is to look at the quantum side of things and of course also at the company side of things. And I think here Planckian does very interesting stuff because they are offering a new way to scale transmon qubits. So I think that's super exciting. But I also have to say I like the design of the website because you have this very, let's say, unique coloring that also kind of is being used in the photos. So you see the photos are kind of matching to the background color of the website. So that gives it, let's say, a very nice design touch. Here you see basically the founding team and the management team as well as the engineering team. So you see there's quite a couple of people which you also need because at the very beginning you might come up with a concept which is very core, right? Like one key idea, this conveyor belt technology, but then you also have to prove it at some point. So you need to implement hardware, you need to run tests, you need to have cryostats, chips, and so on. And that's where things are becoming already more complex. Of course, it's not a super huge team yet. As you can see, though, there are a couple of people already working on this from within Italy in all the different layers of the company. But we don't, for example, see yet, I think, we don't see yet, for example, a CFO or something like that, because it's still, let's say, in the stage where, okay, they have now proven in this experimental setup that the system seems to behave as they had in their mind originally as an idea, and the next step will then probably to be scaling up this whole thing. And as you scale up, of course, you need to collect more funding, and then you also have to increase the team size. So come build with us, and then of course there's here an offer to check out their job openings. And I think, I don't know if that's somewhere, I don't see it here, but as far as I understand, they are a spin-off of the University of Pisa, so they are based in Italy, let's say, probably with the physical team. And then I don't know how it looks on the algorithm side, but that's as far as I understand it. So that's, let's say, a short company overview of Planckian. Again, I think a very interesting technology add-on for qubits, for superconducting qubits. So maybe something to, let's say, keep in our mind, to keep watching, as we see that, let's say, the big players are betting still a lot on superconducting qubit platforms. I hope you liked this video. If so, please make sure to subscribe to this channel, as probably there's a lot more for you to discover. Also, looking at the other videos might be interesting. There's more about superconducting quantum companies in our Hidden Quantum Champions playlist as well. And if you have some, let's say, if you're looking for strategic insight on the quantum market, if you want to stay up to date with the developments because you're a founder in one of those companies, because you're managing one of the departments, for example, superconducting quantum computing department, and you want to stay up with what the market is doing, check out the link down in the video description. Thanks for staying all until the end. Make sure to stay hydrated, and I'm looking forward to see you in the next one. Until then, bye bye.